Morning to one and all. Uh, Let me come back to the next session of detection, estimation and detection. That is the best linear unbiased estimator, otherwise called as BLUE. Okay, BLUE. It is otherwise called as. Till now, we have discussed something regarding minimum variance unbiased estimator. So now we will come across this best linear unbiased estimator. In short, we can call this as BLUE. Okay. So what I want to discuss is, in the previous case, that just like in MVU estimator, if MVU estimator can't be able to found for a particular reason, that means the sense means if for a particular reason, if it is very difficult to find the MVU estimator, for example, if the PDF are not known, or or the probability density function are not known, or computation becomes too tedious. So in that condition, it is a reasonable to look for some other approach, and a common approach is to restrict the estimator, that is to be linear in the data, and the find estimator that is unbiased and has a minimum variance. Okay, that means if the estimator or if the MVU estimator is too tedious for some particular reason, that means that if the MVU estimator to find the MVU estimator becomes too tedious. Too tedious means, in the sense means, for some particular reason it is very difficult to find the minimum variance unbiased estimator, just like if the PDF are not known, or if the computation is too tedious. Under that condition, there will be a reasonable approach for finding out the minimum variance unbiased estimator, and that for the common approach is to restrict the estimator to be linear. The first point, to restrict the estimator to be linear in the data. The second point is find the estimator that is unbiased, and the third one is has minimum variance. Okay, that's the things what I had to discuss here. The best linear unbiased estimator, that is called as BLUE. That means, as I told you, if the MVU estimator can't be found for some reason, that is, for example, if the PDF are not known, or the computation is too tedious, so there will be a reasonable it is reasonable to look for sub-optional estimator or some other estimator, sub-optional estimator. As I told you, the common approach is to restrict the estimator, to be linear in the data. First point, to be linear in the data. Find the estimator that is unbiased, and the third one is has a minimum variance. So this estimator, which is termed as BLUE, that is best linear unbiased estimator, and can be found and can be determined with the knowledge of only the first or second moments, with the knowledge of only the first or the second moments of the PDF. So that means the complete knowledge of PDF is not needed. So if you know the second first as well as second moment of the PDF, then we can able to calculate the that we call as minimum variance unbiased estimator or the or the blue, okay, can be determined with the knowledge of only the first or second moments of PDF. That means the complete knowledge of PDF is not required. So this is the thing what we are going to discuss in this session. How to find the or what are the procedure for finding out the best linear unbiased estimator, and that theory it is very important. So if you know that that means that equation and all those things only, you can able to proceed for the problematic things. Okay, so let me find how to find the what you call as blue. So two sessions, the part A and part B. In part A, we call this as part A. Let the observation be x of 0, x of 1, x of 2, etc., x of n minus 1, and theta be the unknown parameter, For blue, the estimator is, as I told you, it should be linear in the data. That's the first point. For blue, the estimator is linear in data. That means I can write theta cap is nothing but a0 x of 0 plus a1 x of 1 plus a2 x of 2 plus etc. a n minus 1 x of n minus 1. That in general I can rewrite it as sigma I equal to 0 to n minus 1 ai x of I, or an x of n equal to 0 to n minus 1 an x of n. Okay, I or n, anyway you can take. Okay, in some book it will be indicated as x sigma n I equal to 0 to n minus 1 ai x of I, or sigma n equal to 0 to n minus 1 an x of n. No problem. Okay, so where an's are, or ai's are constant to be determined, for theta cap to be unbiased, we should require this expectation of theta cap should be equal to theta. That is, expectation of theta cap should be equal to theta. In the sense means expectation of theta cap already know it is not but sigma n equal to 0 to n minus 1 an x of n equal to theta. Sigma n equal to 0 to n minus 1 an x of n equal to theta. Okay, that is, I will bring the expectation inside that sigma. So sigma n equal to 0 to n minus 1 an into expectation of x of n, that is equal to theta. I will call it as equation 1. Okay, call that as equation 1. And the variance of theta cap is, that is theta variance of theta cap is variance of theta cap equal to expectation of theta cap minus expectation of theta cap the square, with I can rewrite it as expectation of sigma n equal to 0 to n minus 1 an x of n minus sigma expectation of sigma n equal to 0 to n minus 1 an x of n square. Okay, so that I can rewrite it as expectation of sigma n equal to 0 to n minus 1 an x of n sigma n equal to 0 to n minus 1. I will bring the expectation inside the bracket, inside the sigma expectation of x of n the whole square. Okay, that means I bring the expectation inside the sigma. I think it is clear for you, because already you know theta cap is nothing but sigma n equal to 0 to n minus 1 an into x of n. The second term is of that is e of theta cap square, that also sigma n equal to 0 to n minus 1 an of x of n the square. So in that case I have bring the expectation inside the sigma, that is sigma n equal to 0 to n minus 1 an expectation of x of n the square. So just I will take that a b vector a b a naught a1 etc an minus 1. Then your above expression can be rewritten as, the above expression in the sense means variance of theta cap, which is nothing but the expectation of sigma n equal to 0 to n minus 1 a n x of n minus sigma n equal to 0 to n minus 1 a n into expectation of x of n to square can be rewritten as, that is variance of theta cap should be equal to expectation of A transpose x minus A transpose expectation of x square. Okay, that means A transpose, why I have taken, because you have written A vector A is nothing but a column vector, that is A naught, A1, etc., etc., A n minus 1. So if it is taking this transpose, it will be nothing but sigma n equal to 0 to n minus A n into x of n. That is A naught of x naught, A1 x1, like that. A1 A naught x of 0 plus A1 x of 1 plus etc., etc., A n minus 1 x of n minus 1, like that it will go. Okay, I think it's clear. That is your expectation of A transpose x minus A transpose expectation of x the whole square. Sorry. So let E of x is nothing but E of x of 0, expectation of x of 1, etc., etc., expectation of x of n minus 1. Then your variance of theta cap can be rewritten as expectation of A transpose x minus expectation of the whole square. Okay, I just taken the A transpose outside the that is A transpose outside. Okay, so that changes to expectation of A transpose x minus expectation of x into x minus expectation of x, A transpose into x minus expectation of x transpose. Okay, so that in changes to expectation of A transpose x minus expectation of x into A transpose x minus expectation of x transpose. Sorry, I have written once more again the same thing. So changes to, I will bring A transpose outside, A transpose expectation of x minus expectation of x into x minus expectation of x transpose A, because A transpose or transpose is A. So this the middle term, that is expectation of x minus E of x, expectation of x into x minus expectation of x the whole transpose, I will call that as a C. That is, that changes to A transpose C into A, where C is called as covariance matrix. Call that as equation 2, where C is called as the covariance matrix, and that is nothing but expectation of x minus expectation of x into x minus expectation of x the transpose, whole transpose. Okay, this is the first part. Variance of theta cap is nothing but A transpose C into A. Make it in a box, so that term is very important. That is, variance of theta cap is nothing but A transpose C into A. Next, the thing is the part B. Okay, so part A is over. In that part A, we was able to calculate the variance of theta cap, that is nothing but A transpose C into A. Now we will just see regarding the part B. Let vector A of coefficients is to be determined. A of coefficient is to be determined by minimizing the equation in part 2, that is by equation 2, subject to the constraint of equation 1. Okay, in order to satisfy the of equation 1, in order to satisfy the unbiased constraint, expected value of x of n must be linear. That means it should be linear in theta, must be linearly in theta, or I can rewrite as expectation of x of n is nothing but s of n of theta, where s of n, I call this equation 3, where s of n are known. Okay, where s of n are known. It is clear to you. That is, vector A of coefficient is to be determined. So in order to determine that one, we have to minimize the equation number 2 subject to the constraint of equation 1. So in order to satisfy the unbiased constraint, what we have to do, the expected value of x of n must be linearly in theta. That means I have taken expectation of x of n should be linearly in theta in a constraint in theta. That is, I have taken expectation of x of n is nothing but s of n of theta, where the s of n is being non-value. So using 3 in 1, you just put 3 in 1. Using 3 in 1, what I will get? I will get expect sigma n equal to 0 to n minus 1 a n expectation of x of n 0 to n minus 1 a n expectation of x of n can be written as sigma n equal to 0 to n minus 1 a n expectation of x of n is s of n of theta, that is nothing but theta. So that I can rewrite as sigma n equal to 0 to n minus 1 a n s of n equal to sigma n equal to 0 to n minus 1 a n s of n equal to 1. Okay, so in general that is nothing but a n already you know, it is nothing but a transpose s, that is a transpose a naught a1 a2 etc a n minus 1 into s, that is a naught into s naught, a1 into s1, a2 into s2 etc etc a n minus 1 into s of n minus 1. So this thing I can rewrite it as a transpose into s should be equal to 1. That I will call this as equation 4, where the vector s is nothing but s of 0, s of 1, s of 2 etc etc s of n minus 1, where the vector s is nothing but s of 0, s of 1, s of 2 etc etc s of n minus 1. I think till this thing I think it is clear for you. To find blue, we need to minimize variance of theta cap, which is nothing but a transpose c into a, subject to the condition in equation 4. Subject to the condition in equation 4, I will show that one. Subject to the condition in equation 4, this gives variance of theta cap. Variance of theta cap is nothing but 1 by s transpose c inverse s. S transpose c inverse s, and vector optimum value of a is nothing but c inverse into x s divided by s transpose c inverse into s. I will call that as equation 5. Okay, call this as equation 5. So this how you are getting that is variance of theta cap is nothing but 1 by s transpose. You will be confused for that one. Now how we are getting this one, I will explain that one here. Variance of theta cap is nothing but 1 by s transpose c inverse into s, and optimum value of the vector a is nothing but c inverse s divided by s transpose c inverse into s. Okay, that I will explain that one. 1 minute. Just pause here because we will just explain how we are getting that variance of theta cap as well as optimum value of a. Okay, yes, I am minimizing this one. We stop here. Okay, I'll just see. We will just take this one. Okay, how we are getting that one. Okay, how we are getting variance, so that is variance of theta cap, that is our procedure is to get the variance of theta cap should be equal to what, 1 by s transpose c inverse into s, and vector a, optimum value of vector a is nothing but c inverse into s divided by s transpose c inverse into s. It's not c inverse into s. This is the, so we can see that one how we are getting this thing. um, that is a derivation of scalar blue. Okay. So to minimize variance of theta, I'll just write here. To minimize variance of theta cap equal to A transpose C A, subject to the condition it is not necessary that you should include this thing in the part B session. That is why I have explained you in separately. Okay, no need to write this thing. You can directly take the values of variance of theta cap and the optimum value of A. So how this is getting, only I am explaining here. No need to include this session in the while deriving the equation for blue. Directly you can take the values of variance of theta cap and optimum value of A. Okay, so subject to the constraint, it is not condition, subject to the constraint A transpose into S will be equal to 1. We use the method we use the method of Lagrange multiplier. Okay, method of, I think you heard that one, a Lagrangian multipliers. Okay, so the Lagrangian function J can be written as Lagrangian function J becomes, or can be written as, J is nothing but A transpose, just you see that one, A transpose, this is the Lagrangian function CA plus lambda into A transpose S minus 1. Okay, so already in the previous session we have discussed one equation that you just verify that in the I think somewhere else we have discussed the equation for like this, that is dou by, write that one, that is gradient, that is dou by dou theta transpose A theta divided by dou theta is nothing but, is nothing but 2A into theta. Okay, that is why this we have discussed in the linear model. Discussed in linear model of properties. Okay, linear model of properties. So you just verify that I am utilizing this here, just utilizing this here. Okay, so the gradient with respect to the what you call as a gradient with respect to A, we can write this one, that is gradient with respect to A with respect to A, okay, is given by dou J by dou A. It is in a similar manner, that is 2C, I think it is A plus lambda into S, okay. Setting this equal to 0 vector and solving the what you call as you just set this to equal to 0 vector and just solve this, we will get, that is, I will just write on setting setting this equal to, this means dou j by dou I. Okay, this equal to the 0 vector, and solving the above produces what you will get. I can obtain the values of A. Is not, that is 2CA plus lambda S can be made equal to 0. That is 2CA equal to minus lambda S, or A is nothing but minus lambda by 2 C inverse what? S. I think it's clear. It's not. A equal to minus lambda by 2 C inverse into S. So the Lagrange multiplier lambda is found using the constraint equation. Okay, I will write that one. The Lagrange multiplier lambda is found using the using the constraint equation as what? A transpose into into S. It's not A transpose into S becomes equal to what? Minus lambda by 2 A transpose C inverse S, which is equal to 1. So that in general you can write as minus lambda by 2 equal to what? 1 by what? S transpose 1 by minus lambda by 2 1 by, sorry, this is nothing but S transpose. No, it is not A transpose, it is S transpose. Sorry, this is S transpose. Okay, 1 by S transpose C inverse into C inverse into S. Okay, minus lambda by 2 equal to 1 by, is correct now? 1 by S transpose C inverse into A. Okay, so that the gradient, right, so that the gradient is 0 with the constraint satisfied for what? With the constraint satisfied for what you will get? You will get A optimum. It's not A optimum. That is A is nothing but C inverse S, because lambda by 2 already you know, because in this equation, that is minus lambda by 2 is nothing but 1 by S transpose C inverse into S. Sorry, A is nothing but minus lambda by 2 C inverse into S. Okay, that is 2CA is equal to minus lambda S. So we are getting A is nothing but minus lambda by 2 C inverse into S. So minus lambda by 2 you calculate. That's nothing but 1 by S transpose. So 1 minute, I will call this equation as star. Okay, you just verify the equation star. That equation star you are getting A equal to minus lambda by 2 C inverse into S. So here in equation double star, I will call this equation double star. You are having minus lambda by 2. That is nothing but 1 by S transpose C inverse into S. So minus lambda by 2 is nothing but 1 by S transpose C inverse. So A optimum value of A is nothing but C inverse S divided by S transpose C inverse into S. This is nothing but use just substitute the double star in star. You will get optimum value of C A. So this is how we are getting the A optimum. Okay. And the variance of theta cap also you require. The variance for the value of A is found from that is variance of theta cap is nothing but A transpose optimum C A optimum. So that you will get S transpose C inverse C inverse into S. That is A transpose optimum is nothing but S transpose C inverse divided by S transpose C inverse into C. This C only. A transpose is divided by, directly I am writing here. Okay, S transpose C inverse S the whole square. Because A transpose optimum is that is A transpose optimum. Since A transpose optimum will be what? What will be that? C inverse S transpose divided by S C inverse S transpose. Okay. Then next is this C. Again A transpose A optimum is that C inverse S divided by S transpose. So we will get this one. Are you getting? So common term we will delete. So variance of theta cap. No need to write this one here. If you want you can write, no problem. But don't elaborate the expression. 1 by S transpose C inverse S, it can be cancelled. So S transpose C inverse and C got cancelled. So you will have S transpose C inverse into S. So it will be S transpose C inverse into S. 1 by S transpose C inverse into S. In this manner you are getting variance of theta cap. These two things I had directly taken and bring in that equation. Okay, so clear how we are getting the A optimum and a variance of theta cap. Okay, so I'm just minimizing this one and proceed with our things, that is where we have stopped. We have stopped A optimum is nothing but 1 by C inverse S divided by S transpose C inverse into S. Clear? So in general you can calculate that. I call it as equation 5. So in general you get the theta cap is nothing but S transpose C inverse into X divided by S transpose C inverse into S. So that is nothing but 6. That is nothing but our blue. Okay, 1 minute. I'll just verify whether it is correct or not. Yeah. So the blue is nothing but theta cap is nothing but S transpose C inverse X divided by S transpose C inverse into S. Okay, and the minimum variance is nothing but our variance of theta cap is nothing but 1 by S transpose C inverse into S, and minimum variance is 1 by S transpose C inverse into S. That I will call this equation 7, and we will get expectation of theta cap. We observed that expectation of theta cap is nothing but expectation of S transpose C inverse X divided by S transpose C inverse S. So that you will get S transpose C inverse into expectation of X divided by S transpose C inverse into S. So expectation of X is nothing but S into theta. S transpose C inverse S into theta divided by S transpose C inverse into S, that is nothing but theta. So in general we can write expectation of theta cap is nothing but theta. Okay, expectation of theta cap is nothing but theta. So this is the thing what we have discussed here. So in order to determine blue, we require the knowledge. What all knowledge we require? We require S, or the scaled mean, that we call this as the scaled mean. We require the knowledge of, first one is S, that is the vector S, or the scaled mean. The second one is the covariance matrix C for the first two moment, covariance or the first two moment, but not the entire PDF. First two moment, but not the entire probability density function. Okay, and this is something regarding the blue. We can proceed with the one or two problems related to this blue in the next video lecture. Okay, thank you.